We've talked about three different types of energy so far, kinetic and potential from gravity and potential from elasticity, but there are actually many more types of energy. Those are just the three that we do calculations with in physics at this level. We do at least need to be aware of the other types of energy though, especially when we get to an idea called the conservation of energy. So for now, let's group those energies that we've talked about so far. The kinetic, gravitational potential, and elastic potential energy into one group that we'll call mechanical energy. And what separates this from the other type of energy, non-mechanical, is that we're looking at big things, big motions, big movements. So we're not looking at the movement of individual atoms within an object, we're looking at the object itself and its motion, or its position relative to the ground, or how stretched out or how compressed it is. We'll call these things mechanical energy, and the non-mechanical would include the other types of energy, such as heat, light, sound, chemical potential, and nuclear energy. Now a little more detail on each of these other types, since we haven't heard about these before. Heat, or thermal energy, is really just the movement of atoms. In chemistry, you probably would have heard about the kinetic molecular theory, which just says that all matter is made up of these tiny particles and that they're constantly moving. And we know that when they move faster, we experience that as a warmer temperature. And when they move slower, that is a cooler temperature. Now again, this is on a very small level, the movement of individual atoms and molecules, and so we put it in the non-mechanical energy category. Light also carries energy. The amount of energy depends on the color of light and how bright the light is. Sound will carry energy as well, or sound will be a form of energy. Again, this has to do with moving atoms and molecules. When you hear a sound, that sound has traveled to you by vibrations of air molecules traveling through the air. So these air molecules are colliding with each other, and that sends the signal on down the line. Chemical potential energy has to do with that electromagnetic force that we looked at earlier in the class. When we have bonds between atoms, we call those molecules, or at least groups of atoms, not necessarily molecules, there is energy associated with those bonds. When we form bonds and when we break bonds, we use energy to do that, or sometimes we have energy released when we do those things. The last type of energy is nuclear energy, which we could just as well call mass or matter. You've all heard the equation before, E equals mc squared, Einstein's famous equation. Well, the meaning for that is energy is equal to the mass times the speed of light squared. This is just a conversion ratio between the mass in kilograms and the energy in joules. Basically what it says is that we can take matter and turn it into energy. And the equation tells us how much energy we get for a certain amount of matter. Things like the sun or a nuclear power plant do exactly this. They convert matter into energy. And we get, of course, a lot of energy because we're multiplying by the speed of light squared, speed of light being 300 million meters per second. Square that number and multiply it by your mass in kilograms. That tells you how much energy in joules we're releasing. So those would be very, very large numbers. Now, energy is what we would call a conserved quantity. And in physics, when we say that something is conserved, what we mean is that it's a value that stays the same over time. So when we say that energy is conserved, that means that the total amount of energy is going to remain constant. It stays the same over time. With one stipulation, we have to be talking about the total amount of energy in an isolated system. A system just meaning whatever collection of objects it is that we're looking at. So we have to make sure that we don't have objects entering or leaving our problem halfway through, or our system halfway through. And we have to be sure that there are no outside forces that are going to have an impact on this. So if I'm looking at, say, how two two pool balls move when they come together. We say that energy is conserved in that situation, but that isn't necessarily true if, or that isn't going to be true, if halfway through the problem I grab one of the pool balls with my hand and fling it across the table. Well, my hand wasn't part of that system originally, so that would not be an isolated system. That's where this doesn't work. We can express that mathematically as the equation at the bottom here. We get that sigma symbol, sigma meaning the sum of our energies initially is equal to the sum of our energies finally. And it's all those different types of energies that we talked about on the last slide. So we've got the mechanical energy and the non-mechanical energy. If we add those different energy types all together, that number remains constant throughout our problem. Now, where the energy is, what form it's in, that can change. Some of our potential energy from gravitation may turn into kinetic energy, but the total amount of energy doesn't change. And this very important idea is called the law of conservation of energy. Now let's look at an example of that situation. Here we have pictured the initial and final state of a block sliding down a ramp. Initially, we have our block at rest up at the top of the ramp. And in our final state, the block is at the bottom of the ramp and it's moving. In this situation, the ramp is the only object that's part of our problem. The ramp and the block are the only objects part of our problem. Conservation of energy says that the total energy in that initial state is equal to the total energy in our final state. Now let's think about what types of energies that we would have there. Initially, our object, our mass, the block here, is up high. It has the potential to fall down or to slide down. That goes along with our description for gravitational potential energy. It's not moving up there, so it doesn't have any kinetic energy. And there's nothing stretched or compressed, so we don't have any elastic potential energy. Now the block itself has some amount of chemical energy in there, and there's some temperature there, so there's some amount of heat energy. But we're going to focus mainly on the mechanical energies here, again, because that's what we can do calculations with. At the very end, we have our block at the bottom of the ramp. It's at a height of 0, so we can't go any lower. We don't have the potential to fall any more, so we have no gravitational potential energy. We do have movement, though. Movement goes with kinetic energy. As it has slid along that ramp, we have experienced friction. And just like when you rub your hands together like this, you have friction between your hands. You start to feel your hands get warmer. Well, the same thing happens in this case. Friction causes some of our energy to turn into heat energy. Now also, when you rub your hands, you can hear that. And when this block is sliding down the inclined plane, you can hear that as well. So initially, we've got potential energy from gravity. In our final state, we have kinetic energy. We also have energy from heat and energy from sound. Now in this class, we aren't going to look at how to calculate the energy from heat or from sound. So either we would have to be given that information, these two values, and use it to solve for the rest that we have equations to solve for. Or we'd have to be looking at a situation where friction makes only a small amount of energy turn into heat. So we make the assumption that, well, basically, these two numbers are so small that they don't have a big impact on our problem. Let's pretend that they're 0. And we just lost the screen here. Let's go back. There we go. So that's what we'll do here. We'll just cross these out. We'll say that the amount of energy that we're turning into heat and sound is very, very small compared to these values. Now that's a good assumption to make if we have smooth surfaces there, or some of the problems you might see in the textbook would even say we have a frictionless ramp, so that'd be a good assumption there. It would not be a good assumption if it's extremely rough. You might be able to tell this if the block maybe starts moving, if you give it a push, but then it comes to a rest halfway down the ramp. That's a lot of friction. That's not going to be a good assumption to make there. Now we can substitute in equations for potential energy from gravity and kinetic energy. And those equations are going to be mass times gravity times the initial height for our potential energy from gravity on the initial side, and 1/2 mv squared for the kinetic energy on the final side. From here, we can solve the rest of the problem. We'd be given some information about mass, maybe, or about initial height, or about final velocity, and we'd be solving for whatever value wasn't given to us. So let's look at an example problem like that. So here's that frictionless surface I was talking about. We have a child who starts from rest, sliding down a frictional slide from an initial height of 3.50 meters. We're looking for the speed at the bottom of the slide if we assume she has a mass of 25.0 kilograms. So when we write out our given information, it says she starts from rest. That tells us initial velocity is 0. From an initial height of 3.50 meters, so height initial, 3.50. Mass is 25.0 kilograms. We're looking for her speed when she gets to the bottom of the slide. At the bottom of the slide, she'd have a height of 0, so we'll say height final is equal to 0. And the question is, what's her velocity, or what's her speed at the bottom of the slide? So we are looking for V final on this problem. So in this situation, we have the same situation as we did with the diagram a moment ago. And so we know that our initial energy total is equal to our final energy. Final energy total. And initially, we had just potential energy from gravity. That's initial. In our final state, we have just kinetic energy. Oops. Keep my formatting the same here. Kinetic energy final. We can then plug in an equation for potential energy from gravity, which is mass times gravity times height, and we're on the initial slide, is equal to our kinetic energy, which is 1/2 times mass. We're on the final side, so that'll be final velocity squared. Now it's worth noting here that on this equation, we have a mass in every term of this equation. So as long as mass isn't 0, we can just divide everything by m, simplify our equation a bit. So let's do that now. If we had 3 terms in here, say we had plus some other energy term, we'd need to divide that one by m as well, which only makes sense if we would have m in all 3 terms. So we get g times hi is equal to 1/2 times v final squared. I'm looking for v final in this problem, so I want to isolate that. Right now I have 1/2 times v final squared, so I'll go ahead and multiply both sides by 2 and get 2ghi is equal to v final squared. And to get v final just by itself, no square, we'll square root it. And we end up with v final is equal to square root of 2 times gravity times initial height. An equation which doesn't have mass in it, which is maybe a little counterintuitive. You would think that the bigger kid sliding down the slide goes faster, or the adult sliding down the slide would go faster because they're heavier. But it turns out that that term cancels out in this equation. So mass doesn't affect this problem. Now we can plug in and solve for our final velocity, which is 2 times the acceleration of gravity, 9.80 meters per second squared downward, times our initial height, which is 3.50 meters. And we get a final velocity, when we round it to 3 sig figs, of 8.6 0.28 meters per second. Now again, to solve these problems, we either need to be given information about how much energy turns into heat and sound, or we need to have a situation where we can assume that those values are very close to zero, or we can ignore those values. Otherwise, these problems aren't solvable with what we know right now in physics. So the last point here is just a reminder that mechanical energy, the ones that we can make calculations with, will not be conserved in the presence of any friction, really. But we'll make the assumption that mechanical energy is conserved unless we have a significant amount of friction. So if we have two surfaces that are very smooth, we'll say, that's close enough for us. So we'll make the assumption that heat and sound and any other forms of energy associated with friction are zero. In the case of, say, a very rough block, like a sanding block sliding along a piece of wood, we have a lot of energy in the form of heat that's being lost, not lost, but changed into heat and then spread out from there. And so that makes these problems much tougher to solve. We'd have to know something about how much energy was lost in the form of heat. That's it for mechanical energy. Thanks for watching.